Hello, everybody. Today we're doing question 2 in chapter 3, and this one's going to be a bit of a long one because it's got 3 parts here. So for each of these potential functions, we're going to be determining the period of oscillation as a function of the energy. When a particle of mass m moves in fields with that potential energy. So for each of these, we're going to be using the same base equation, which is the equation for the period that you can get by integrating the energy conservation equation. Now for part A, let's start plugging in for our actual value of the potential function in this case. And in particular, because we are going from 0 to x naught, that means x is always positive within this integral, so we can just write ax to the n instead of absolute value of x to the power of n. Next, we're going to start working on solving this integral. So we're going to do a substitution. Specifically, we're going to let the nth root of e over a times y equal x. We can plug this in. The reason we're doing this is to get these constants, e and a, out of our integral as much as possible. So now we have an integral from 0 to 1 of e minus ey to the n to the negative 1/2. We'll be able to take out that negative 1/2 power e as well. So now we have an integral from 0 to 1 minus y to the n, all to the negative 1/2 dy. And it should be dy in this line as well. Now we're going to do another substitution. Y to the n is equal to u. We can work out how that relates the differentials. So dy equals 1 over n, u to the 1 over n minus 1 times du. Now we're going to plug all of this in. So we have 4 over n times the square root of n over 2e times the nth root of e over a. And the integral from 0 to 1 of 1 minus now u to the power of negative 1/2 times u to the 1 over n minus 1 times du. And this integral, you might notice or want to learn that this is the beta function with values of 1/2 and 1 over n. And the beta function is related to the gamma function, which is related to the exponential. And so we'll write our answer in terms of these gamma functions. So we have t equals 2 over n times the square root of 2m over e times the square root of e over a times gamma of 1/2 times gamma of 1 over n all over gamma of 1/2 plus 1 over n. And we actually know that gamma of 1/2 is equal to the square root of pi. That's a whole other story. We can plug that in to further evaluate. And that will be the end of part A. We're going to go on and do part B and C as well. For part B, we have that the potential is equal to negative u0 divided by cosh squared. That's the hyperbolic cosine of alpha x. And we're just going to immediately plug this in to our starting integral. Now, in this case, we know that e is going to be negative. So when we factor it out, we have to factor out the negative 1/2 root of the absolute value of e, so that we don't accidentally take the square root of a negative number there. Now we're going to do substitution of constants to make our notation a little bit simpler. We're going to let beta squared actually equal u0 over the absolute value of e. And this is going to simplify our notation within the integral just a little bit. Next, I'm going to focus just on this integral and work on solving it. So now I'm going to write this term in the denominator. What I did here was I multiplied the top and the bottom by cosh alpha x, and that entered the radical expression. So now the beta squared, the cosh squared are separated. And I missed the power of 1/2 in the denominator in the previous line. So don't be alarmed by that. The power in the denominator on that line should be positive 1/2, not negative 1/2. So what I've done here now is I've added and subtracted 1 in the denominator so that I can use the hyperbolic trig identity to write this integral in terms of sinh in the denominator and cosh in the numerator. Now, doing a hyperbolic trig substitution, we're going to be able to write this without any hyperbolic trig functions at all. So we get a leading constant and the integral of 1 over 1 minus z squared to the power of 1/2 dz. Now I'm going to take a moment to look into this constant at the upper bound of the integration, which will be negative 1/2 power of b squared minus 1 times sinh of alpha x naught given our condition for alpha x naught being at the maximum of this object's motion, we know that that's when the energy will equal the potential energy. So we find that cosh squared of alpha x naught is actually equal to beta squared. And because sinh alpha x naught is then equal to beta squared minus 1 square root, we get that z naught is equal to 1 exactly. It simplifies our integral slightly. And we can now go on to do a regular trig substitution with z equals sine of theta. dz equals cosine of theta d theta. And plugging these in, we have an integral from 0 to pi over 2 of 1 d theta. That's because the cosine from the differential exchange cancels with the cosine from the denominator. So this means that if the integral's value is pi over 2 alpha, we can scroll back up and determine what we need to pair that with to get the final period. And we multiply that previous value by 4 because we want not just the distance from the maximum to 0, but the distance from the maximum to 0 and back and back and back. So now we're moving on to part C. And again, it is the same exact strategy, except this time our potential is u naught tangent squared of alpha x. For this problem, we can start by multiplying the top and bottom by cosine of alpha x. Using this substitution, we can write that cosine squared alpha x is 1 minus z squared, and sine squared alpha of x is z squared, and the cosine alpha of x in the numerator disappears through the transformation of the differentials. Now we can rearrange and write this in terms of just one coefficient in front of z squared. We can factor out the square root of e, which in this case is positive. Now here I'm introducing beta squared as u naught over e, similar to before. And now I'm going to do another substitution. It's going to be standard trig substitution. And then we'll be able to evaluate this integral. So if we reduced it to an integral from 0 to theta naught d theta, everything else cancels. So we just need to figure out what is theta naught. Starting at the beginning, we have z naught equals sine of alpha x naught, and e equals u naught tangent squared of alpha x naught, and beta squared equals cosine squared of alpha x naught divided by sine squared of alpha x naught. This means that beta squared equals 1 minus z squared all over z squared with z naught. That means z naught squared is equal to 1 over beta squared plus 1. So if 1 plus beta squared to the 1/2 times z naught equals sine of theta naught, then theta must be equal to pi over 2, because the left-hand side is equal to 1. So now we have our time interval, m over 2e under the square root, multiplied by 1 divided by alpha times 1 over the square root, 1 plus beta squared, times pi over 2. And now writing beta back out in terms of u naught and e, and multiplying in order to have the full period, we get that the period is square root of 2m over e plus e naught times pi over alpha, and that's it. Thank you.